Hi, my name is Eva, and this is my lab report for Lab 4 of Physics 2, and it is about magnetic braking with Faraday's law. So, a little introduction to what's going on in the lab. The purpose is to explore the interaction between a falling bar magnet and a conductive aluminum foil tube. And the objectives were to record observations of a bar magnet falling through a conductive aluminum foil tube, create a computational model to simulate magnet tube interaction, and compare these simulation results to the data that I got from running the experiment in real life. So in real life, I got from my experiment that it took the magnet 2.042 seconds to fall through the aluminum foil tube. And with the code that I made, it took 1.155 seconds. So there were a couple of key observations that I got from this lab. So I noticed that the magnet descends more slowly through the tube because of electromagnetic resistance. The induced currents were present in the aluminum tube. The magnet entered through the top and exited through the bottom of the tube. The fall was slower and possibly deviated from a straight trajectory when it's in the aluminum foil tube as opposed to just falling free. And the currents generated in the tube opposed the changing magnetic field of the falling magnet. So there were a couple of key physics laws that I used in this experiment to understand what was going on in the real life experiment, as well as to work with the code that we were given. So I used Faraday's law of induction, Lenz's law, the magnetic fields and forces principles, the Biot-Savart law, and Newton's law of motion. And these equations on the right are used to understand what's going on when I'm running the lab and to develop and interact with the code of the computational model. So for the real life experiment, the system was the bar magnet and the surroundings were the aluminum foil tube and the earth. And I assume that air resistance is negligible and the tube remains stationary during the experiment. Um, I recorded also the experimental parameters that I used, like the tube length, tube inner diameter, magnetic dipole movement of the magnet, and the average fall time. So basically the steps that I took to do the experiment were identifying the north end of the magnet, dropping the magnet through the center of the aluminum foil tube, then recording the time that it took for the magnet to fall through the tube. And I repeated this 5 times just to maintain consistency. And I only used non-ferrous materials so that I would avoid interference because ferrous metals are magnetic and this would distort the results of the experiment. Then I also developed code and worked with that to see what would happen kind of in a perfect world ideal situation if I was dropping the magnet through the aluminum foil tube, which is shown above, like a simulated tube. It's turned to the side to fit in the slide better, as well as a graph of velocity versus time of the magnet falling through the aluminum foil tube. And then when I ran all of this code, it said that the time in the tube in seconds is 1.155 seconds, as opposed to the other value that I found from doing the experiment in real life. So I also noticed with the graph that there was a high initial downward velocity just after the release. Then the velocity decreases and stabilizes while the magnet is in the tube, and it increases again once the magnet exits the tube. And I noticed a constant velocity region in the tube, and this means that the net force is zero at that point because magnetic drag is balancing gravity. Also, the initial negative slope indicates that gravity is being opposed by magnetic forces, and the final positive slope after exiting the tube shows the magnet accelerating under unopposed gravitational force. So the measured fall time, as opposed to the computational model, was slightly higher than what I found from the model. There are some sources of error that could have happened, like human timing inaccuracies while recording the time, air resistance, and minor external forces that weren't accounted for, and environmental or electromagnetic interference that isn't accounted for in the model. And if you run the code, you can see in the simulated magnet that the color intensity represents the magnitude of the current in each ring. And if you reverse the magnet, this would flip the induced current direction, and this would result in a reverse magnetic field configuration, but the same opposing force effect applies. And the system remains symmetrical in behavior, and this is assuming uniform tube conductivity and geometry. So if the just some discussion items, if the resistivity of the conductor were reduced to near zero, this, according to Ohm's law, would lower means that there would be a higher induced current for the same EMF, and a larger current would generate a stronger opposing magnetic field, which would mean a greater magnetic force acting upward on the falling magnet. And if holes or slots were cut in the tube, then interruptions along the conductive path would break or weaken the closed current loops, which would cause smaller or complete currents to form, and the magnetic force opposing the magnet's fall would decrease. So the magnet would fall faster. Thank you very much.